In question 26, we're asked to calculate the density of an object. We're given the volume and we're given the mass. So I'm going to use the formula density equals mass over volume, and I'll plug in the 32.8 grams on top. And then I want to go ahead and divide by the volume. So I'll divide by 4.75 milliliters. When I did this, I got 6.905 263 grams per milliliter. But we only have 3 sig figs with these values, so I'm going to report my final answer as 6.91 grams per mil. So whenever you're asked to solve for mass or volume and you're given some kind of density, you should definitely consider using density as a conversion factor. So the density of the lithium is 0.53 grams per 1 centimeters cubed. So I wrote it in that familiar conversion factor format, looks like a fraction. I flipped it as well, remember, because you can always flip your conversion factors. The 1 still stays with the centimeters cubed, and the 0.53 is with the grams, but now it's in the denominator. So we have 2 versions of the density conversion factor written there. You're going to start it the same way you did all your other conversions. So it's a cool technique in that it uses and enables you to practice more conversions. So they're asking us to solve for volume, and they gave us the mass. So I'm going to start with mass. So 1.20 times 10 to the third grams. And I'm like, it'd be great to get rid of grams. And I want to go to volume. They weren't too specific about the units, so I'm going to keep it simple and go to centimeters cubed, because that's what my density has. And it looks like we're going to need the 1 all the way over here, because the 1 is still going to stay with the centimeters cubed, and the 0.53 is next to the grams. We're going to see that the grams cancel, and we're left with units of volume. So in your calculator, 12,000 divided by 0.53, and then that gives us a value of 2.264 times 10 to the third centimeters cubed, but sig figs always, right? Our conversion factor is not exact because it's a density. So we're going to have to go with 2 sig figs on our final answer. So I'm going to do 2.3 times 10 to the third centimeters cubed. So I'm going to start with my mass, my standalone number, 719 grams. I'm asked to calculate the volume in milliliters of a 719 gram sample of mercury. So I want to get rid of grams and go to milliliters. Up here, I set up my 2 versions of my density conversion factor. The first one is direct, and the second one is the flipped version. So I'm going to use the second one. I'm going to say 1 mil has 13.6 grams. Grams will cancel with grams, leaving us as mils. So I'm going to do 719 divided by 13.6, and that gives me 52.9 milliliters. And it's appropriate to have it in milliliters because mercury is a liquid. Here, we're starting with 6.54 grams of acetone. We need to get rid of grams, and we were asked to convert to volume in milliliters. So I'm going to use the second version of my density conversion factor. And I know it says milliliters, but milliliters and cubic centimeters and centimeters cubed are equivalent. So this right here is equal to 1 milliliter divided by 0.7857 grams. So I kind of just did that in my head. And that's perfectly fine. I don't need to see the work on that. So grams will cancel grams, leaving us with milliliters. And so the answer here is 8.32 milliliters. So this problem does an awesome job illustrating the power of conversion factors. We're given the volume of gas inside a little fuel tank. And we're also provided with the density of the gas, and we're asked to solve for the mass of the gas in kilograms. Now, looking at the units of density, they don't match our initial volume units. So here we have cubic centimeters, or we might be thinking about milliliters over there. But we're starting with liters. And then over here, we're in kilograms, but in our conversion factor, in our density, we have units of grams. So we're going to have to do quite a bit of converting to make this work out. Let's set it up. I'm going to start with the standalone number, the number that's not a conversion factor. So 1.45 liters. And I'm thinking, I want to get rid of liters. But I can't do anything with it over here. So maybe I need to turn my liters into milliliters. So I'll do 1 liter has 1,000 milliliters. Now you can do the next step in your head. I'm going to write it out just for completion's sake. So in the next part, I'm like, I need to get rid of milliliters and turn that into centimeters cubed. And now milliliters cancel milliliters. And then I'm seeing I can use this conversion factor. I can get rid of my volume finally by putting centimeters cubed in the denominator, and I can go to grams. So I'll do 0.710 grams in 1 centimeter cubed. Now that's gone. Almost there. We got to get to kilograms, so we might as well do that. So we're going to get rid of grams. I'm going to do 1 kilogram has 1,000 grams. So at the end of the day, when I multiplied across the top and then divided by 1,000, I got a value of 1.0295 kilograms. And I knew it was kilograms because everything else canceled out. We have 3 sig figs, 3 sig figs. So I'm going to go with 3 sig figs. So final answer will be 1.03 kilograms. So in this problem, we have a lot going on. We're asked to calculate density, and we know that density equals mass over volume. The student measured the mass directly, so we're good to go with mass. However, with the volume, we're given the length, width, and height of a rectangular metal bar. So we're going to have to take a second step here and calculate volume first. So I'm going to use the formula volume equals length times width times height, and I'm going to put in 2.4 centimeters times 1.0 centimeters times 8.53 centimeters. So I'm just multiplying all of my length measurements together. And that gave me a value of 20.472 centimeters cubed. Important to remember here that sig fig rules tell us that we shouldn't round this value to the end. I know it's tempting. You're like, oh, I just have 2 sig figs. but keep this whole value until we're done with the calculation. And actually, I'm going to make note of that. So remember, when you're doing those multi-step problems, you think about how many sig figs you have at each step, but you don't take it all into consideration until the end. So here I'm thinking, yeah, I got 2 sig figs if the problem were to end now, but we're not done. So I'm going to use this formula. I'm going to do 52.7064 divided by 20.472. And I got a density of 2.57456 grams per centimeters cubed. And then I started looking at sig figs. This volume, even though I wrote it with all these digits, it only had 2 sig figs, right? Because the initial measurements only had 2 sig figs. So this final density is going to be reported as 2.6 grams per centimeters cubed. Alrighty, one thing that I would recommend as the problems get a little bit more complicated here is label all of the information as you read through the problem. So a piece of silver metal weighing 194.3 grams, so I'm going to label this with M for mass, is placed into a graduated cylinder containing 242 mils of water. The volume of the water now reaches 260.5 mils. So it sounds like they're using some kind of volume by displacement to get the volume of this piece of silver. So I'm going to label this as volume with a little subscript of I for initial, and this one is going to be VF for my final volume. Calculate the density of the silver. So we want density at the end of the day. So first let me tackle the volume issue. We just want the volume of the silver if we're trying to solve for the density of the silver. So I'm going to use the fact that volume final minus volume initial is going to give me the volume of the silver. 260.5 milliliters minus 242.0 milliliters gives me a volume of, what is that, 18.5 milliliters. So that's the volume of the silver that I need to carry into the next part of the problem. I'm going to use the formula density equals mass over volume. The mass I labeled earlier, so I'm going to grab that number and plug it in. 194.3 grams divided by 18.5 milliliters. And so after I divided that, I got a value of 10.5027 grams per milliliter. Let's check sig figs. So here, since it's subtraction, I'm going to look at decimal places. I have 1 decimal place here and 1 decimal place here, so it's fair to keep 1 decimal place there. This volume then has 3 sig figs with its 1 decimal place. So now I have 4 sig figs divided by 3 sig figs. My final answer can only have 3 sig figs. So I'm going to report the density of the silver as 10.5 grams per mil. And you can also change the grams per mil to grams per centimeters cubed if you want. A lot of times people associate the milliliters with the liquid and the centimeters cubed with solids, but I'm not picky. I'll take either one and mark it correct. To determine the density of acetone, a 55-gallon drum is weighed twice. So I'm not really sure what to do with that information yet. Let me keep on reading. The 55-gallon drum weighs 75 pounds when empty, When it is filled with acetone, the drum weighs 437.5 pounds. Alrighty, so now I see where they're going. Acetone is a liquid, and you can't just pour the liquid on the scale to get its weight, right? You need some kind of container to hold it. So they weighed the container when it was empty, and then they put the acetone in it. So this weight right here is the weight of the container plus the weight of the acetone. But I don't care about the container at all, right? So what I'm going to do, it's going to be very similar to volume by displacement. I'm going to take my initial weight, let me use W for weight, and this is my final weight. And if I take the difference between those, then I'll just have the weight of the acetone. What is the density of the acetone expressed in grams per milliliter? Alright, so we're looking for density, and we need it to be in grams per milliliter. Okay, lots going on here. I do need volume. Well, if they filled the 55-gallon drum with the acetone, then I know the volume, right? 55 gallons is a volume. So I'll make note of that as well. So let me calculate the weight first. I'll do weight final minus weight initial to get the weight of just the acetone. So 437.5 pounds minus 75.0 pounds gives us a weight of 362.5 pounds. So this is just the acetone by itself because we got rid of the mass or the weight of the container. So looking ahead, pounds is not going to work. We need it to be in grams. So I'm going to take the weight of the acetone, 362.5 pounds. And they're very kind, well, in some ways, right? They gave us this conversion factor. So we can go directly from pounds to grams. So put pounds in the bottom and grams on top. And it says 1 pound has 453.6 grams. So pounds will cancel with pounds. And when I did that, I got a mass in grams of 1.6443 times 10 to the 5th grams. Alrighty, and actually let me put a big M next to that to remind me that this is the mass I'm going to use when I finally get to calculating my density. Next problem. The volume is in gallons. I need my volume in milliliters. Again, they gave us a conversion to use, so let's start with that. So 55.0 gallons, and I want to get rid of gallons. And I'm going to go to liters. 1 gallon has 3.785 liters. Gallons cancel with gallons. Let's take it one step further. Let's go to milliliters. So I'm getting rid of liters and going to milliliters. And there's 1,000 milliliters in 1 liter. So if I do 55 times 3.785 times 1,000, I get a volume of 2.08 175 times 10 to the 5th milliliters. So I'm going kind of extreme here with all the sig figs because of that rule. Keep all the digits until we get to the end of the problem. Let me label this with a V for volume. Now I'm ready. So now I have the correct units. I'll do mass over volume. So I'll take our mass right here, the 1.6443 times 10 to the 5th grams, and I'm going to divide by 2.08175 times 10 to the 5th milliliters. And when I did that, I got 0.789864 grams per milliliter. We do need to look at sig figs. So much going on. This was all multiplication, right? So 4 sig figs over there, 3 sig figs, 4 sig figs, exact. So it looks like we only have 3 sig figs. So my final answer, the density of the acetone is equal to 0.7. So 3 sig figs, I'm going to have to round up. So I'll do 0.790 grams per mil. So here we're asked to calculate the mass of a stainless steel cylinder. We're given information about its height and radius. So I used the formula for volume of a cylinder, and I got this really quite long number out of it, but I didn't want to round because, again, we're not supposed to round till we're done with the problem. Don't forget that this squared applies to both the 1.88 and the centimeters. So in terms of units, you have centimeters squared times centimeters, which gives us centimeters cubed. So since this volume value has units of centimeters cubed, and I'm trying to get rid of that, I think I can use this version of the density conversion factor. That'll get rid of the centimeters cubed and leave me with grams. I talk a lot about not rounding until you get to the end. And on a problem like this in particular, you type in all this, you hit enter. The number is there. So once you have this number, all you have to do is hit times 7.75. And your calculator will recall this number. You don't have to type it in again. It'll save you a second. Centimeters cubed cancels centimeters cubed, and I got 1.578 2766 times 10 to the 3rd grams. However, it looks like we're only going to have 3 sig figs because of the density. So I'm going to report this as 1.58 times 10 to the 3rd grams. The density of water is about 1 gram per mil at room temperature. And anything that has a density less than 1 gram per mil will float on top of the water. So that's why wood and styrofoam float on top of water, because their densities are less than water. Same thing with the vegetable oil. Its density is only 0.93 grams per mil. So I expect it to be on top of the water layer. So I'm going to label this top layer here that's marked as C. I'm going to label that one as vegetable oil. Water has an intermediate value, so I'm going to put that in the middle. So layer B is going to be water. And then the density of mercury, since it's a metal, it has a slightly higher density. That's going to be the bottom layer here. So Hg, which is our elemental symbol for mercury. So it seems like we're given the length, the width, the height of a rectangular bar. So I know that I can use these dimensions to calculate volume, and then they give us mass. The question is, will this rectangular bar float in water? So the only way to determine if something's going to float in water is to know its density. So given the dimensions of the rectangular bar, I can calculate its volume. And then I also have its mass, so I can use the volume with the mass to calculate the density. So I'm going to do 8 centimeters times 2 centimeters. Don't want to lose any sig figs there. 2.00 centimeters times 2.00 centimeters. So that gives us a volume of the bar of 32.0 centimeters cubed. Now for density. Density is mass over volume. So I can do 362 grams divided by 32 centimeters cubed. That gives me a density of 11.3125 grams per centimeter cubed. Looking at all the information, I have 3 sig figs. So let's say the density of this bar is 11.3 grams per centimeter cubed. Critical information if we're trying to figure out if it's going to float or not. So water has a density of 1 gram per mil. If something's less than that, it'll float. Well, it doesn't seem like this bar is going to float. 11.3 grams per centimeter cubed is a much larger density. So I'm going to make note of that. This bar is going to sink in water. The next question is, will it float in mercury? And mercury has a density of 13.5 grams per mil. So we can use the same reasoning, except with a different value. If it's less than 13.5 grams per mil, it's going to float on the mercury. If it's more than 13.5 grams per mil, it'll sink below the mercury. So 11.3 is less than the density of mercury. So I'm going to say that this rectangular bar will float in mercury or on mercury.